So momentum is a vector quantity which is defined as the mass of an object times the object's velocity. And so it's denoted by this p. So notice, since mass is a positive scalar, the momentum is always pointing in the same direction as the velocity vector. And of course, being a vector, we can do all the usual vectory things to it, such as vector addition, separating it into its x and y components, which is useful many times for analyzing collisions and stuff. So also notice that we can rewrite Newton's second law in a different way using momentum. So the net force on an object is also equal to the rate of change of the object's momentum. In other words, the time derivative of the object's momentum. And you can see that this is the same thing because momentum is m times v, and if the mass of the object stays constant, which many times it does, then we can move it out of the derivative, and so it just becomes the mass times the derivative of the velocity, which we know to be the acceleration. So let's say we have a system with two objects, and only these two objects. And so there are no external forces. The only forces are the internal forces that the objects are exerting on each other. By F21, I mean the force that object 2 exerts on object 1. And similarly, F12 denotes the force that object 1 is exerting on object 2. By Newton's third law, we know that these two forces are equal and opposite. Now we can look at the total momentum of the system. So the total momentum of a system is just all the momentum of the particles in it added up. So a total momentum here is the momentum of object 1 plus the momentum of object 2. And so if we want to find the rate of change of the total momentum, then that's the same thing as the rate of change of the momentum of object 1 plus the rate of change of object 2's momentum. And so we just found out that the rate of change of the momentum of an object is the same thing as the net force on the object. So we can replace the derivative of P1 and P2 by the net force on object 1 and the net force on object 2. So what's the net force on object 1? Well, the only force acting on object 1 is the force that is being exerted by object 2, which I denoted by F21. And then on object 2, the only force is the force from object 1, which is F12. But we just found that they are equal and opposite, so they add up to 0. So therefore, the rate of change of the total momentum of the system is 0. In other words, the momentum stays constant. Maybe not necessarily the individual momentum of object 1 and object 2, but if you add the momentum up, they always stay the same. So this is called the conservation of momentum. If we have a system with no external forces on it, then due to Newton's third law and how all the internal forces are canceling out, the total momentum is staying the same. So again, it's important to note that this is the total momentum of the system, not the individual momentum of each particle. So we just proved the conservation of momentum for 2 particles. So let's look at a system with 3 particles with no external forces. So we have 3 particles and each one is exerting a force on the other 2 particles. And so by Newton's third law, each of these forces has an equal and opposite pair. And so again, we can write out the total rate of change of the momentum by just adding up the rate of changes of the individual momentum of the particles. And then we can replace the derivative of momentum for each particle by the net force acting on that particle. And so if we write all of the forces out, we'll see that each one has an equal and opposite pair. So, the force that 2 exerts on 1 is equal and opposite to the force that 1 exerts on 2. So those two add up to 0. 3, 1 is equal to 1, 3, and then 2, 3 is equal to 3, 2. So again, all the internal forces are canceling out, and so the total rate of change of the momentum is 0. So what if we had the same system, but this time there's an external force on object 2? So again, if we wrote out all the individual forces, all the internal forces would cancel out, and then we'd just be left with the external force. So the rate of change of the total momentum of the system is equal to the net external force. And by the definition of momentum, we know that's equal to mass times acceleration. So for the rate of change of the total momentum, it's equal to the total mass of the system, all the masses of the particles added up, times the acceleration of the system. This is nothing new. This is just Newton's second law, how we've already been using it. We take the net force to be only the external forces, and then if we were looking at a system with multiple particles, then instead of just m, we added up all the masses of the individual particles. So let's look at one example of a collision, which is just when two objects bump together. Object 1 and Object 2. Object 2 is at rest, and then Object 1 is moving towards it at some velocity v0. And then they bump together, and they stick during the collision and move with the same velocity, which is what we want to find. So this type of collision, when the objects stick together, is called a perfectly inelastic collision. And so we can easily solve for their new velocity using conservation of momentum. So first notice that a system consists of the two objects, and there are no external forces on the objects. So therefore, their total momentum is conserved. So again, their total momentum is the momentum of object 1 plus the momentum of object 2. The total momentum before the collision is the same as the total momentum after the collision. And before the collision, object 2 was not moving, and so since its velocity was 0, its momentum was 0. So before the collision, only object 1 had any momentum. And after the collision, they both have their own momentum. So initially, object 1 is moving with a velocity v0, and then after the collision, both are moving with a velocity v. And so we can factor out the v on the right side, and then just move the sum of the masses over. And so we've solved for the new velocity vector that the objects are going to move with after colliding and sticking together.